Hello, everyone. I'm sure many of you have heard of the fooling set technique. It is a very basic, very simple technique to show lower bounds on the length of communication protocols. In this talk, I will show you how this very basic, very elementary technique is actually very powerful and is still giving us new lower bounds even after so many years. The specific lower bounds that we will talk about are lower bounds for CAS channels or noisy CAS channels, which I shall also call noisy radio networks. And the definition is very simple. You have a bunch of wireless devices in the same room that are communicating with one another. Because these devices are wireless, when one of them sends a message X, then the same message X gets sent to all the other devices in the room. And because these devices are in the same room, when two of them try to send messages at the same time, then the signals collide and none of the messages go through. So all the parties actually receive a dummy symbol bot in this case. So one party is speaking, the message goes through. Two or more parties or zero parties are speaking, everybody receives bot. This is the CAS channel. And what we want to do is we want to see what is the effect of noise on the CAS channel. So consider the noisy CAS channel, which is exactly the same, except that every round has correlated noise, stochastic noise in it. So if one party was speaking, the right answer would be the message X that is sent. But because of this noise, with some small probability, everybody receives a different message or maybe receives a bot in this round, even though one party is speaking. And again, if say two parties are speaking, then the right answer is the dummy symbol bot. But because you have noise, maybe somebody receives, maybe all of them receive zero in this round with some constant probability. So this is correlated stochastic noise. Everybody receives the same symbol, but it may be incorrect with some small probability. Noise can only hurt our channel. So if you have a protocol initially that was taking T rounds, now it can only take longer than T rounds. And we want to see what is the slowdown that is caused by such stochastic noise. Clearly, the best slowdown one can hope for is constant. The best result that we can show is you take any protocol of length T and you can run the protocol even if there is noise at the cost of a constant factor in the number of rounds. So now your protocol is a constant times T, but it does the same thing even in the presence of noise. The worst thing that you can hope for is the noise slows it down by a factor of log n, where n is the number of parties in the system. And this is the worst thing because what you can do is you can always repeat each round of the protocol log n times. And then because the noise is random, except with probability polynomially small in n, the majority bit will be correct. And you can union bound over all the parties and all the rounds and everything is polynomial in n. So log n is the worst possible slowdown we can hope for. Constant is the best possible slowdown we can hope for. And we want to know what is the right answer for this CAS channel. We already know from prior work that if the initial protocol is restricted to be non-adaptive, which means that even before the protocol starts, you know exactly when each party will transmit. You don't know what they're going to transmit, you don't know the exact bit, but you know exactly which rounds they're going to transmit in. And we know that if you have such a non-adaptive protocol, there is a way to run it over the noisy CAS channel that loses the non-adaptivity. So the new protocol is adaptive, but it's only a constant factor longer and does the same job. So if you start with a non-adaptive protocol, you can get a noise-resilient adaptive protocol with only a constant slowdown. And today we are going to talk about the general case. We're going to show that if your initial protocol is general, if it is adaptive, then the slowdown is actually the worst possible log n. So we can go from the best possible to the worst possible by removing this restriction. And this is our main result. Again, we want to show a protocol that takes some T rounds over the CAS channel and has a log n slowdown or takes T log n rounds at least over the noisy CAS channel. And this shows the worst possible slowdown between CAS and noisy CAS. And the key lemma when we are showing this result is we will define the beeping channel and we will show that the separation between the noiseless CAS and the noiseless beeping channel is also log n, which is also the worst possible. So there is no noise here. It is just the noiseless CAS versus the noiseless beeping channel that I'll define next. We will show a separation between these two of log n. And it is simple. I will not cover it, but it is fairly simple to see why this implies a separation between CAS and noisy CAS. So this is the result that we will show in this talk, and this is what we actually get in the paper. And actually, this result is much more general than what it seems. You can actually define a broad class of channels called the F channels. This class includes, for example, all the threshold channels. It includes the parity channel. It includes many channels of interest. It includes the CAS channel. And you can show that you can put any F channel here. And all of these F channels are, beeping is weaker than all of these F channels. You have a protocol for each F channel. You have a protocol over that F channel, such that running it on beeping requires at least a login overhead. Okay, so this lemma can be generalized significantly, but we shall only work with this version. We want to show the separation between CAS and beeping, but first let us define the beeping channel. To define the beeping channel, I want you to think of it as just the OR channel. Again, you have your wireless devices in a room. They all send bits, but this time the channel outputs the OR of all the bits sent. If everybody is sending 0, then the OR is 0, and therefore everybody will receive 0. This is the one case. The other case is when some of these parties are sending 1, then the OR becomes 1, and now everybody receives a 1 in this round. The beeping channel, therefore, is just the OR channel. And we want to show a separation between CAS and beeping, which means we want to show a protocol that takes T rounds. Again, there's no noise anymore. It's all noiseless. T rounds over the CAS channel, such that any equivalent protocol over the beeping channel has at least T login routes. Let's do that. The protocol we shall use is actually a protocol for the following function. You have your N players. You divide them into root N groups of root N players each. And you are promised that each group has either exactly 1 player with the input 1 and the others are 0, or exactly 2 players with the input 1 and the others are 0. And you have to output which is the case for each group. So you have to output root N bits, 1 for each group, saying whether that group has 1 or 2 players with input 1. This is the hard function. And note that this can be solved in root N rounds over the CAS channel, because in the CAS channel, if 1 player is transmitting, you get the bit. If 2 players are transmitting, you get a bot. And all you have to do is you go group by group, and in each round you have all the players who have 1 in that group transmit. If there's only 1 such player, you will receive the bit. If there are 2, then you will receive a bot. And you will know which is the case for each group in root N rounds. Okay, this is the function. There is a CAS protocol for it in root N rounds. And now I want to show that any beeping protocol for this function has root N times log N rounds, at least. As promised, the way we shall do it is we shall use the fooling set technique, which is a very basic technique that I will now explain in the 2-party communication model. There are only 2 parties, Alice and Bob. It's not the beeping channel. It's a simple 2-party model where Alice's inputs are denoted by X and Bob's inputs are denoted by Y. And a fooling set for a problem in this 2-party model is just a set of inputs, xi, yi, indexed by I, that have the same output. So the correct answer for each of the pairs of inputs in this set is the same, say 0. And you also have the property that for all I different from I prime, whenever you take 2 different pairs in the set and you cross them, so you take X from one of the pairs and Y from a different pair, then there is a cross that you can generate for any 2 pairs of inputs, such that the output for this cross, the correct output for this cross, is different. They were all 0 to begin with, but as soon as you start crossing, your output is now 1. Okay, this is what a fooling set is. And the claim is, if you have a fooling set of some size, let's say S, then you can conclude that any deterministic protocol for that function must have length at least log S. And the argument is the following. You show that if you have a protocol of length T, then it breaks the set of all inputs into 2 to the T rectangles. And you show that each rectangle can only have 1 element from the fooling set. Let's see why. Suppose you have a protocol of some length. Alice sends the first message in the protocol. This message can either be 0 or 1. And therefore, this message partitions the set of inputs into 2 parts. 1 top rectangle here, where Alice sends a 0. And 1 bottom rectangle here, where Alice sends a 1. Then you have your next round where Bob is starting. Again, he receives Alice's message, and he either sends a 0 or a 1, which he can use the previous message to determine which is the case. And again, this partitions further your two rectangles into four rectangles. And this is the rectangle where Alice sent a 0, and now Bob also sends a 0 in response. This is 0 and then 1. This is 1 and then 0, and this is 1, 1. So you can keep going. You get that if you have protocol of length t, then you will partition this input space into 2 to the t rectangles. And now you can argue that each such rectangle, let's say this one, can only have one element from any fooling set. It can only have one pair from any fooling set. Why? Suppose you have this rectangle that has two pairs. Suppose it has x1, y1, and it has x2, y2. Then because this is a rectangle, it also must have the cross pair x1, y2. And we know from the definition of fooling set that the output for x1, y2 is different from the output for x1, y1, and x2, y2. But the outputs cannot be different if they're the same rectangle. So this is a contradiction. So you get that if you have a fooling set of size t, then you must have s, then you must have at least s rectangles, which means you must have at least a length of log s. A fooling set of size s implies the length lower bound of log s. Okay. The only problem is that this technique does not work for randomized protocols, because a randomized protocol is allowed to fail on some inputs. So it is okay for x1, y2 to be in a rectangle if it is one of the inputs that it fails on. And moreover, it does not work for the beeping channel. It only works for two-party or similar models. And these are big problems because we want to use this technique to show a lower bound for randomized protocols on the beeping channel. But let us ignore them for now. We will deal with them later. Let us see if our function actually has a fooling set at all or not. The answer is yes. So our function is you have these n players divided into root n groups of root n players. And each group either has a 1 or 2 players with input 1. And the claim is there is a fooling set of size root n to the root n for this function. The fooling set is very simple. You take all the inputs that have only 1, 1 in each group. So these brackets here denote groups, and you see that in each of the root n groups, there is only one player with the input 1. And this is a fooling set because all of these have the same output, which is every group has 1. But you take any two of them and you cross them so that the second input, the red input here, comes from this hybrid and the remaining comes from this hybrid. Then this set of inputs and the remaining come from this set of inputs. Then in the hybrid, you have a group with 2 players who have the input 1. And this must have a different output. So you have a set of inputs with the same output such that for any pair, you can cross them and you can get an input with a different output. This is the definition of fooling set. The size of this fooling set is each group you can decide where to put the 1. You have root n groups, so it is root n to the log n. And if the fooling set technique were to hold, then this would give a lower bound of log of this, which is root n log n, which is what we want. The only problem, again, is that this technique does not hold. It only holds for deterministic protocols, and only those deterministic protocols that are not on the beeping channel. For deterministic beeping protocols, it may not hold. Okay. So we need to get around these two problems. For the first one, we actually show that you can generate not just one, but many hybrids from the same pairs of inputs. So here we decided to take our cross on this group, but we could have done that on any of these groups, and we would have still have an input with a different output. So any two inputs in our set actually gives rise to many, many bad inputs, many bad crosses. And the sheer number of these bad crosses allow us to go from deterministic to randomized lower bounds. And the second case, the second problem, which is that the technique does not work for beeping, we are able to still make it work by using the additional structure that we have in our system. In our system, we know that whenever you take a hybrid, you only change the input of one party. And this locality where only one of the parties' input actually changes in this hybridization process allows us to generalize it to the beeping model. I'll not go into the details, but this uses the number of hybrids and this uses the locality of each hybrid. And with these two things, you're able to show that the beeping protocols for the function that we talked about must have length at least root n log n, even if they are randomized. And this shows a separation between CAS and beeping of log n. It follows that you have a separation between CAS and noisy CAS of log n. And this is our main result, that CAS noise slows down the CAS model by at least a factor of log n. So that's the talk. Thanks for listening. Thank you.